right. I think this is problem set 14. I think it's at least homework 14. And for this one, the most important thing that we need to keep in mind is this formula right here, which you can find in the textbook. I know in high school I learned it with an R instead of a K here because it represents the rate. An easy way to remember this is just remember PERT. It doesn't have any real meaning other than just kind of helps you remember that in the order that it's all written. But that always helped me. But that's the equation that we're going to be using, or the formula rather, that we're going to be using for most of these questions, I believe, including this first one. So let's go ahead and take a look. It says a culture contains 600 bacteria initially and doubles every 25 minutes. Find a function that models the number of bacteria after t minutes. Okay, well, if in this case we need to use this function where p of t is the number of bacteria after a certain number of minutes, p naught, or just p, I will be using p naught down here to represent that, is going to be our starting number of bacteria, so it's going to be 600. Then it's all times e to the k times t. In this case, I know that my bacteria doubles every 25 minutes. So I know that it's going to be 1200, right, and equals that first thing. I know it's all going to be 1200 bacteria. That's going to equal my initial bacteria times e to my rate times the current number of minutes, which is going to be 25 in this case. And now we just need to go back and solve for k, and then we can plug all of our known values back into here, except for t, obviously, because that's the variable with which our function is respecting. So here I'm just going to undo that 600 there, because we want to isolate that k. It's just some algebra. 1200 divided by 6 is, or divided by 600 is 2. And honestly, we could have just known that because I know that this is the doubling time. So I know that the ratio of this, no matter what numbers I was using, I know that if I'm looking for when it's doubled, it's always going to end up 2 equals e time to the power of kt. But that's not something we super need to worry about right now. In this case, we know t is 25. In order to get this down here on its own, I'm going to undo this with a natural log. So I'm going to take the natural log both sides, and it turns into the natural log of 2 equals k times 25. So our rate, k, equals the natural log of 2 divided by 25, right? Because I just divided to cancel that out. And now that I know k, I can plug that back into this equation. We know our initial number of bacteria, and now we know our rate. Remember that e is a number, just like pi is, so it's not something that we need a specific value for because it is its own value. So I'm just going to plug that in. We know p naught is 600 times e to the power of our new k value, over 25 times t. And that's all they're looking for that function there. So I know for the homework, it asks for a specific format of it. So it asks for like 2 different formats, I think. One of them is something like, oops, I didn't mean to do that. Why won't it undo? That's no fun. It won't let me do anything. Because I'm trying to press the eraser and it won't let me click it. Uh-oh. Okay. There we go. I don't know what that was about. I was just trying to fix because I wrote an R instead of a K. So I think they have it with our t divided by c. And so in that case, oops, it undid all of that. So in this case, if they're looking for like t divided by c, c in that case would be our 25, and our k would technically be the natural log of 2. But our k is technically this whole term right there. So depending on how they ask for it, you might need to sort of look at that differently, but that equation is still the same. Now we want to solve for the time t that it will take for the culture to reach 3,600 bacteria. So that's when p of t equals 3,600. So I just take the formula we found and I set them equal to each other. I plug it in. All right. So I'm going to get this. And then now we're solving for t. It's a capital T I could use there this time. But for right now, it doesn't really matter because I just know that this is what we're solving for. If I divide this out, 3,600 divided by 600 is going to be 6. Equals all of that again. And again, to get rid of this e and to take a look at the stuff up there to isolate it, I'm going to take the natural log, both sides. That's going to get me this. So now if I want to find t, I'm going to multiply by this and divide by this, or just divide by the whole fraction, which is the same thing really, just to get t by itself. So I'm going to get 25 times the natural log of 6 divided by the natural log of 2 equals t. So our answer is whatever this is. I think for the homework you have to write that out in decimal form just because of the formatting. And I will go ahead and plug that into a calculator just so we can see kind of what that looks like. So that looks like about 64-ish minutes is the answer. Okay. Our next question is a similar one, but I suppose not too similar. These are all a little different, but they all rely on that same formula. So it says an unknown substance produces 7,200 counts per minute on a Geiger counter at a certain time, and only 800 counts per minute 12 days later. Determine the half-life of the substance. Well, we don't know at what time this is, but we know that we're starting here and we end up coming down to here. So I'm going to use this as our P naught in this function here. So I'm going to use 7,200 as my P naught. So I'm going to say P of t equals 7,200 times all of that. And we know that 12 days later, it produces 800 counts. So now my P of t, when t is 12, is 800. So I'm going to plug that in. And now I need to solve for that rate again. So now I'm going to do 800 divided by 7,200, which is just 8 divided by 72, or I think that is 1/9. Feel free to correct me if I'm wrong there. And that's going to equal this. And just like before, we take that natural log and we isolate our k. So that rate is the natural log of 1/9 divided by 12. Okay, now that's not our answer, right? That just helps us fully form this equation. We want to find what the half-life of the substance is. So the half-life is going to be determined by whatever t equals when our P of t is half of our original count there. Or as I said earlier, that ratio is going to be that. So it's when, I could set it like this. This is the function for determining half-life. And it's the same thing really, right? Because half of 7,200 would be 3,600. So if I wanted to use it that way and just plug it into that original function, I then divide both sides by 7,200. And it turns into, this is going to be a 1/2. This disappears and cancels out. And you see how I just got to the same thing? I'm basically just skipping steps when I just jump to that ratio there. But it's important to understand that relationship for some later questions. So I'd really recommend giving that some extra thought. It's a little tricky to explain if you don't see it right away, but I hope that made some sense. Anyway, we know our k value, so I can plug that in up here. So it's going to be natural log of 1/9 divided by 12 times t. And now I just need to solve for what t is, because remember, e is its own number. So now I'm going to go backwards, not backwards, but take the natural log to isolate up here. And now I just isolate t, so I'm going to multiply by 12 and divide by this natural log. And that is what our t is going to be. So that should be our half-life, whatever number that is. And I'll go ahead and plug that into the calculator as well. So it's going to be 12 times natural log of 1/2 divided by natural log of 1/9. And that has a half-life of approximately 3.79 days. And that's pretty close, I think. This next one says a particular organism doubles in population every 6 days, beginning now with a population of 5,000. So they just told us right now its doubling time is 6 days, and it has a starting population of 5,000. So we know P of t equals 5,000 times e to the kt. Yeah, and we know that doubling time is 6 days, so I know it would take for it to be 10,000, so I know that ratio would end up being 2 equals e to k times 6. And we can go ahead and solve for k now. So natural log of 2 equals 6 times k. So k equals the natural log of 2 divided by 6. And there are some equations and formulas that are basically just cutting to this step right here. I don't really bother memorizing them because I think that it's easier to just remember one thing and be able to figure your way out to the rest of them. But if you do better with just memorizing the formulas, I would definitely recommend looking those up and giving yourself some time to study those. Now we plug that back in. So we want to know what the time it would be for the population to quadruple in size. So that would be when our P of t is 20,000. Or when the ratio that ends up over here is 4, right? Because it's quadrupling. And we see that when I divide this out, this right here turns into 4. So I'm looking for when 4 equals that, and we can actually plug in our k value since we know it. All right? So that's the natural log of 4 equals the natural log of 2 divided by 6 times t. Undo this. So it's 6 times the natural log of 4 divided by the natural log of 2 equals t. And if I'm right, I believe that actually should just be 12. But let me double check that because I could be misremembering how this works. Make a lot of mistakes. Okay, yeah. This ends up equaling 12 when you plug that into your calculator. Just because of how that works out. Now we want to know what it takes for it to triple. So because of what we've just kind of gone over with that ratio, instead of setting it up and figuring out what 5,000 tripled is and plugging that in, I just know that it has to be 3 equals e to the power of k times t, right? So I'm just going to plug it in like that, except I know my k, and I'm looking for t, and it won't let me erase again. Why is it doing that? Oh, how very frustrating. Okay. So natural log of 2 divided by 6 was what we determined k was. And that k is just a rate for the whole equation, so it's never going to change between whatever ratios you're setting it up, because it's just the equation that models that models what's happening there. So now I've set it up like this, made it a little easier on myself. I know that skipping steps can be a little confusing, but if you're confused on what I did here, it's the exact same thing that I did for the previous one. I just skipped a couple of steps. So if you're not sure what I skipped, I'd recommend rewinding a little bit. Let me continue, right? Because I multiplied by 6 to cancel that out. I divided by natural log of 2. So t equals whatever this is. And let me plug that into our calculator to see pretty exactly what that equals. Because that is not a nice, pretty number. It is instead a long decimal. Okay. And let's keep going. So suppose you have some substance which has a half-life of 2100 years. How long would you have to wait for 1/5 of it to disappear? For this one, you might look at it and get pretty confused because it feels like we don't have enough information to figure out any of it, right? But remember what I was saying with those ratios earlier? We know that the half-life is 2100 years. So whenever P of t is 2 times whatever P naught is, right? So if you're stuck on that ratio bit, I'll kind of explain a little bit here. So remember that P of t is always going to be equal to P naught times E to the power of K times T. If we're looking for when P of t is double this right here, I can plug that in to that original equation here. And then when I'm solving for like my K value up there, because in this case we know our T is 2100, so I can plug that in. We're solving for K. I'm going to divide by P naught because I want to get rid of it. And when I divide that by both sides, it cancels. So I just get 2 equals this, which is what I was going to jump straight to, but I think that this might make a little bit more sense for how I got there. And then we can go from here, we solve for K, and then we use that to set up our original equation again. So let's go ahead and solve for what K is. So our K value is natural log of 2 divided by 2100, okay? Which means that we know P of t equals P naught times E to the power of natural log of 2. Okay, so this is what we're using now. And we want to know how long it takes for 1/5 of it to disappear. Remember that P of t is how much of it is remaining. So if 1/5 of it disappears, I know that 4/5 of it will be remaining, which means that the ratio that's going to happen here when I divide this out is going to be 4/5. So divide by that, and I just get 4/5 equals this over here. I hope that makes sense. I know that's really tricky. And then we just solve for t, just like we've been doing. We're going to write it down over here. Sorry if you can hear my dog barking. Okay, and just isolate t. And whatever this is our answer. I'll go ahead and plug that into the calculator once again. Hold on. That doesn't make sense. Uh-oh. I might have made a little mistake because the answer I'm getting is negative, and that just doesn't make logical sense. Although it's also entirely possible that I set the question up poorly. Steps should be correct though. Oh, you know what? I messed up here when explaining the ratio. So if P of t equals 2 times P naught, Yeah, I did a poor job of explaining that, and I'm not sure how to fix it. We shouldn't end up with a 2 here, because that should be doubled. It should be a 1/2 instead. And that's the mistake that I made, because we're plugging in the half-life. So when that final value is half of it. Oh, yeah, that's what I messed up. It's not going to be double that, because we're looking for when it is half of it. Goodness, I don't know how I messed that up. I'm so sorry. I hope me switching that up isn't too terribly confusing, but I have to go fix it everywhere that I wrote it wrong. But if we're looking for the half-life is how long it takes for, if they gave us the half-life is how long it takes for half of the substance to disappear, right? So half of it will be remaining. P of t is what is remaining, so P of t is going to be half of that original substance. If you then plug that into the function, like so, and then divide, those cancel, we get just this here. Okay, and then we solve it like I was doing. Let me just fix that. Glad I caught that. And now if I plug that into my calculator, divided by 1/2. Good. That is a positive answer, and it makes sense. It's going to be a little over 676 years. Okay. And that makes sense because for 1/5 of it to disappear is going to take less time for a half of it to disappear. So it makes sense that it's less than our half-life. If you got an answer larger than the half-life, then you might want to go back and do some of your math. You might have set it up as 1/5 instead of 4/5. I did that when I was first starting out. Not with these exact numbers, of course, but similar conceptually. Yeah, if you were looking for more than half of it to disappear, then it would make sense for that to be greater than the half-life. But in this case, we're not. So our answer makes sense. Let's try this next bit. It says a small quantity of radon gas, which has a half-life of 3.8 days, is accidentally released into the air in a laboratory. If the resulting radiation is 60% above the safe level, how long should the laboratory remain vacated? Oh, I don't love that the program's freezing. That's not my favorite. Not my favorite at all. Okay, there we go. I don't know what has been such a big issue with it. It works fine when I'm not recording, so maybe it's my recording software. Yeah, so we want to figure out how long it's going to take for it to return to a safe level. So remember our equation here. Okay, we know it has a half-life of 3.8 days. So I can say that 1/2 is going to equal this, right? Just based on that ratio again, because we don't know that original level. We just know the ratio is going to be 1/2. And then I solve for k like usual. Okay, so then k equals this here. And I plug that back in. And I know it is this. Okay. And now I know that the current radiation is 60% above a safe level. So again, because we don't know those exact values, we do want to use ratios, which makes it really good that they've given us this percentage. So I know, let's say our safe level is a level of maybe 10, right? 10 what? I don't know. Doesn't matter. Just say 10, because it's nice and easy to work with. 60% above that, right, is going to be 16, because 60% of 10 is 6. So 60% above the safe level of 10 is going to be 16. if I'm waiting for it, so right now it is at 16 out of 16 is that current level, which we're considering our original level right now. And I want it to get back to a safe level of 10 out of 16. That's the ratio we're looking at. Okay? So I'm going to set it up so that it is 10 out of 16 like that. And then, of course, we know our k value, so we just need to find t, and that'll be our answer. So then, once again, solve like usual. And you could reduce that to, I think that reduces to 5/8. This might be a little easier to process. Okay, so then t is going to be 0.8 times the natural log divided by natural log. And whatever this is should be our time. I'm going to plug that into a calculator, just make sure it makes sense. And it says the laboratory should remain vacated for about 2.5 days for it to remain to a safe level. All right, and I'm not sure that I did a great job of explaining the ratio bit, but I'm also not sure how else to explain that, so if that doesn't make sense, I'm really sorry. I'm not super sure how else to put it. But we could think of it, oh yeah, there we go. So again, we said our hypothetical safe level is 10. 60% above that would be 16, right? So that would mean that we want it to return to 10. So our P of t would be 10. And our the original level that we're starting at before it starts degrading is 16. So in order to isolate that up there, I'm just undoing this, right? So it turns into, those cancel, equals that. And that's exactly what I wrote up here, right? This is just kind of how you set that up and think about it. Again, I'm skipping steps a little bit in my head there. So I'm sorry if that makes it confusing. But it's a little bit of a habit. Let's take a look at this next bit. It's a lot of questions with this formula. Luckily, I think after number 7 here, we move on from that. So let's take a look at number 6 and work through it. It says, recently uncovered was a wooden spoon that was made about 2,300 years ago. If the half-life of this carbon element is about 5,730 years, what percentage of the original carbon would you expect to be left in the bowl today? I think it's carbon 14. I'm terrible at science. I don't remember anything chemistry related. But it's the same type of problem once again. So we know that it was made about 2,300 years ago. We'll say that 2,300 years ago is when t equals 0. So today, t equals 2,300, right? We know the half-life is about that. So we're considering that ratio is 1/2. This is what we know, right? We know that this is going to be true because that's the half-life. So the half-life of the carbon after this amount of time, blah, blah, blah. So let's solve for k. So k equals natural log of 1/2 divided by 5,730. And now we want to know what percentage would be left in the bowl today. So we want to know what this is going to be. So I'm going to say what is left. And we still just like don't know that ratio, right? We're looking for the ratio. So I'm going to plug in my k value. And for today, we know our current t value is going to be 2,300 because that's how much time has passed. And this you just plug into a calculator, and whatever the answer is our answer. Sort of. Of course, when we plug it into a calculator, we're going to get big long decimal. So remember how we turn decimals into percentages. Let me go ahead and plug this into my calculator just to get the decimal. Okay, so the decimal that we get here is like this. Right, and again, I would type out all of these decimals just to be safe, make sure that the homework accepts it. So if I have this long decimal for my answer, that's the ratio, right? And that just means move that decimal point over, it's a little over 75%. Right, just like normal. Sorry about that. So that would be our answer here. So it'd be a little over 75%. Come on to this next one. This is a measure of barometric pressure, where T is miles above sea level. So we want to know the pressure at sea level. Well, if T is miles above sea level, then if we're at sea level, we are not above it at all. We're just right at it. So T is going to equal 0. So we want to find P of 0. Plug that in. Get 29.92 e to the this. Well, I know negative 0.2 times 0 is just 0. So that's e to the power of 0, which is just 1. 1 times 29.92 is just 29.92. If I want to find it 3 inches above sea level, same thing. T is inches above sea level. If it's 3 inches above sea level, T is 3. Just plug it in. And at this point, you would just plug that into your calculator. I know 3 times 0.2 is going to be 0.6, right? And then same thing for 8 inches above sea level. Same deal, or I guess I should be using approximately instead of an equal sign. Okay. And then I'm going to plug both of those into my calculator. So let's see. E to the negative 0.6 times 29.92 is about this. Oops, that should be a 2. Okay. And then same thing with that one. So E to the negative 1.6 times 29.92 is about this. And boom, that's all there is to that. Now we're moving on out of that equation. And yeah, so number 8 says exponential functions in this form. So exponential functions where f of x equals a of x for all a of greater than 0 are continuous on the interval negative infinity to positive infinity. We want to use that to find our following limits. So this function here is 3 to the power of x, which is in the form a to the x. So I know it's continuous, right? I know it's continuous on all intervals, right? Because negative infinity to infinity. And if it's continuous, that means that the limit is just whatever it plugs in, right? Because there's no jump, there's no holes, there's no discontinuities. So it's just whatever it plugs in as. So it's just 3 to the x. And it's just that. That's all I have to write. For this next one, this is not in the same form, right? And if I plug in a 0, I will get 1 minus 1 over 1 minus 1. I'll get a 0 on the denominator, and I'll get a 0 on the top. So it's an indeterminate form. So what I have to do instead is I have to manipulate this a little bit. So if I have the limit as x approaches 0 of this function, let's go ahead and manipulate that. It might be hard to see, but I recognize that this is actually a perfect square. I know that's going to be 9 to the x minus 1, or perfect difference of squares, sorry, times 9 to the x plus 1. Right? Because when I multiply these together, I'm adding my exponent, so I get a 9 to the power of 2x. Which means that these are just going to cancel. So, oops, and I forgot my limit declaration. You always want to include that, at least when doing work for school or anything, because if you forget to write that, well, first of all, it's just a good habit to be in, but if you forget to write it on any exams or anything, it will most likely get you points off. They'll mark that wrong. Right? So now it becomes this, which is in the form a to the x, right? We've just got an extra add-on, but it's still, the actual function is still in this form and is therefore continuous. So now if I plug in that 0, that's going to be 9 to the power of 0 plus 1. Anything to the power of 0 is 1, so it's just 1 plus 1, or 2. If we come down here, this is also technically in that form, although it is an x squared. So we should still be able to just plug that in, I believe. So I know 1.1 squared is just 11 squared with a decimal in it. 11 squared is 121, so it's going to be 1.21 and then minus 2. And these are my answers. All right, just a few more questions to go. For number 9 here, we are given this function. We want to find all the critical numbers on this interval. So let's go ahead and take the derivative of cosine of x to 1/3. Obviously, we're going to use chain rule because we've got something special happening in there. So let's say this, and v equals that x to the 1/3. I know chain rule tells me that the derivative of my chain is going to be the derivative of my outside times the derivative of the inside. Right, so the derivative here, I know it's x to the 1/3, so it's going to be 1/3 in front times x to the negative 2/3. And I'm going to rewrite that as this, just for personal preference. Does not matter, really. You could leave it like this, or you could rewrite it like that. I will note that rewriting often gives you extra room for error, but this is just personally easier for me to read, so I will keep it that way. So we just found that our derivative equals negative sine of x to the 1/3 times that there. Okay. And I want to know when this equals 0. Well, I know it's undefined when x equals 0, but on this interval, x never can equal 0, right? Because it's not included. So on this interval, this function is never undefined, and it will equal 0 whenever this trig function equals 0, right? So we just need to look at when this equals 0, or rather, don't even matter about the sign, just when this equals 0, which means that x to the 1/3, or our cube root of x, has to be something that makes our sine function equal 0. When does sine equal 0? Well, sine equals 0 whenever x equals 0, or whenever x equals pi, or 2 pi, or so on, right? 3 pi, 4 pi, forever and ever. We know 0 isn't on our interval, so we're just going to ignore that. But so we want the cube root of x to equal pi. So if the cube root of x equals pi, well then x equals pi cubed. Okay, so my x can it can equal pi cubed, or it can equal whatever 2 pi all cubed is, so it's going to be an 8 pi cubed. And I could keep going, but I already see that this one is outside of my interval. So this is going to be the only one that falls in our interval, and boom. The rest do not exist. Let's take a look at number 10. This one's got a lot of steps to it, but we're almost done as our second to last question. This one's a little more confusing, but it's not the worst, I promise. It says an open-topped box is made from a piece of cardboard, 16 inches by 20 inches. So I'm going to go ahead and draw my piece of cardboard. Right, it's just a rectangular piece of cardboard. And so it is 16 inches by 20 inches. Okay. And it's made into a box by cutting squares of equal size from each corner and bending up the flaps. So that looks like cutting squares from each side, and then bending up the flaps, right? And that makes sense because this would kind of like fold up, that would fold up, and it would all just come together and make a box. All right, so if the side of the squares is x inches, right? So x, we want to determine the equation for the volume of the box. So I know this length here is going to be that 20 minus, well, I've got an x over here and x over here. So it's going to be 20 minus 2x. And now here, it's going to be the same thing, but with my 16, right? Okay. So now if I fold this piece up, and I fold this piece up, and I fold this piece up, and I fold this piece up to make my box, I'll go ahead and draw out a little box to help us picture this. Cannot draw a straight line apparently. Okay, so the height of that box is going to be x, right? This bit here is going to be that 20 minus 2x, and this bit here is going to be that 16 minus 2x. Okay, so we know our width, we know our length, we know our height, we know volume. It's just length times width times height, so that makes it pretty easy. So our volume function is just going to be all of these things multiplied. You can probably leave it in that form for the homework. I'm not sure. I think I did go ahead and distribute that out. So if we just, I'm going to multiply out that x first. So it's just 20 minus 2x times that. It makes it a little easier to look at for me personally and for me to multiply. So now I just FOIL, and let's see, 10 times 160, 10 times 16 is 160, 20 is going to be 320x, 20 times negative 2x squared is going to be minus 40x squared, negative 2x times 16x, negative 32x squared, negative 2x times negative 2x squared is 4x cubed. So our volume function, and I'm going to go ahead and write this in standard form and combine these like terms. It's going to be 4x cubed minus 72x squared plus 320x. Okay. Now, what we're going to look for is figuring out the largest possible volume, right? So we want to figure out what x value makes our volume the largest. At what point is it at its maximum, which we know how to find maximums, right? We know how to do that using the derivative and figuring out our extreme values, which is exactly what we're going to do. But first, they ask for, if we include the possibility of a volume of 0, then we want to know the largest possible value for x and the smallest possible value for x. Okay, well, let's figure out the domain of our volume function here, and I am going to factor that out really quick because I know I see that a 4x goes into all of it, so that's going to be an x squared minus, what is 72? It's 18x, I believe, and then plus 80. Okay. I don't know if that factors out at all. I could try. Give me one moment to see if that factors. Oops. Oh, lucky us, this does factor out. It gets to be like that. The one that I actually did for the homework was not factorable, so I ended up having to use the quadratic formula, which was not my favorite. But lucky here, it gets to be x minus 8, x minus 10. I'm going to go ahead and double check that. X squared minus, perfect. Okay, so now to figure our domain. Okay, figure out our domain. I know, let's see, if I just kind of use logic, I know that my smallest thing here, my 2x can't be bigger than 16, right? Because if 2x is bigger than 16, then I'm cutting further onto like one side than I can I can do, right? If they're all going to be equal sized squares. So x has to be, so right, if 16 minus 2x is maybe the highest I can go, then that's going to be a 2x equals 16, x equals 8, and we see that here, right? So our x has to be less than or equal to 8, and that could get us a volume of 0. It also has to be less than or equal to 10 because of our other side, but that's also kind of default with our less than or equal to 8, and it can be 0. It has to be greater than 0, right? Or equal to, because we can have a volume of 0 in this case. So based on this, our domain is then going to be inclusive, 0 up to 8. Because if I do a 9, then it doesn't satisfy this condition, even though it satisfies this. So this is our domain. So now we know our smallest possible value is going to be 0, and our largest can be 8. Any higher, and it simply doesn't make sense for like actually cutting anything out. Then based in this domain, looking at this interval, we want to find our extrema. So if I take the derivative of our function, right, I'm going to take it with this, just because that's a little easier to do than this. I'd have to use some product rule, which is annoying. So it's going to be 12x squared minus 144x plus 320. And I should be able to factor out, oh, I can't factor out a 12 from all of that, can I? But I can factor out a 4. I'm just going to do that so it's a little easier to look at. Oh, what is 144 divided by 4? 36. Okay. Then plus 80. And that's pretty ugly. We want to know when this derivative equals 0. Well, it's going to be whenever this equals 0. I think we have to use the quadratic formula for that, which is unpleasant, but that's okay. Remember, our quadratic formula is as follows, where A is this, B is this, C is this, right? Okay, so that's going to be a negative 3. And it doesn't change that I factored out that 4, or it shouldn't in this case anyway. So negative b, well, my b is already negative, so it's just 36, plus or minus the square root of whatever 36 squared is. Oh, that's going to be ugly, isn't it? Okay, so it's that minus 4 times a times c, so it's going to be 320 times 3, right, because 4 times 80 is 320, times 3 is going to be 960, all over 2 times a, so all over 6. 1296 minus 960 is 336, so it's going to be 36, or well, I can divide that out, so it's going to be 6 plus or minus the square root of 336 over 6. And I bet I can pull something out of there. Let's see. I can't, I'm just blanking on factors of 336. Let's break it down nice and easy. So 336, there's obviously 1 in 336, there's 2 and 150, 163 should work. No, 150 gets me 300, 15, so 65, so 168 should do that. Yeah, okay. And then I can go down to 4, and that's going to be 50 plus 34, 84, and I can probably go down to 8, and that's going to get me 42, 16, and 21. And that doesn't break down any further, but I can pull out the 16. Just going to be plus or minus, put that 16 right, because that's the square root of 16 times 21, which is the same as, pull out my 16, that. So I'm going to do that, and it's 4 divided by 6, so 2/3. 21, right? So these are my critical values, and we'll have to see which ones are on our interval, which ones are on our domain. So if x could equal either of this, which one's on our domain? Oh, that's really hard to think about in my head. I am going to pull out the calculator for this just because I'm not great with radicals like that. All right. The 6 plus, oops, I just wrote plus or minus again. The 6 plus 2/3 times the square root of 21 is greater than 8. It's a little over 10 actually. So it is outside of our domain. But the 6 minus 2/3 times square root of 21 is just is greater than 0 and less than 8, so it's in our domain. So we're going to use this one. This is our only extreme point. And just kind of using logic, it's probably our maximum. Let me figure out exactly what that equals with my calculator. That is about right here. Now, that's got to be our maximum, really, just logically speaking. But we need to prove that it's our maximum. So, if we look on that interval, right, I've got 0 up to, and I'm going to still write it like that just because it's easier to. And then from that up to the higher end, right? In order for this to be our maximum, this has to be increasing and this has to be decreasing, right? So that it looks something like that. Let's double check that. So if I plug in a value between here, which would be 1, is a good one. So v prime of 1, and here's my v prime up here, so I'm just going to plug that in. It's going to be 12 minus 144 plus 320. I can see that my positives clearly outweigh that negative, so it's going to be positive, which is increasing. And then a value between this and 8 is 2. 2 is a good one. Nice, easy to work with. 2 squared is 4, so it's 48 minus 288 plus 320. Still outweighs it. Nope. No, it doesn't. Yes, it does. What? How does that work? Hold on. I chose 2. 2 squared is 4. 4 times 12 is 28. Minus 2 times 144. And that's going to be a negative 240 plus 320. But that's positive and indicates that this is increasing. I'm confident I've messed up somewhere, because that simply doesn't make sense. Uh-oh. 2 is greater than this. I try a different value. Maybe let's try 3. I've got 9 times 12. That's ugly. That's going to be... No, that's not going to weigh out either. I'm not sure where I messed up, but I think you get the gist. So our x should probably be about this. That should be our maximum, which is about this value here. Really confused as to where I messed up, though. It's also possible I messed up on my quadratic formula. The process that I was following should be correct. I think I most likely made an algebraic error somewhere. So, oops. Hopefully nothing major. If it is, please let me know. Okay. Maybe I'm just plugging it in wrong. I don't know. Times 12. Oh, well, if I do plug in a 3, actually, it ends up being -4. I definitely messed up somewhere, and it's possible that I just plugged this in wrong, or maybe I miswrote part of it. That's always a possibility. But it definitely should be somewhere around here, maybe slightly bigger. I'm so sorry that I'm messing this up. Anyway, to find the largest possible volume, whatever your x ends up equaling, you just plug back into your actual function for the volume, and that's your answer there. I'm not going to do that now because I think I might have messed this up, and it's kind of pointless just to put the wrong answer down. But generally that should work. Let's go ahead and do number 11. This one I'm confident I'm not going to mess up because it's so short, there's just not much to mess up. Looking at our f prime, I have to take the integral of that. And I can kind of think of this as a 19 times 1 over x. And for 1 over x, that's the same as this. So you can't use the power rule for that because going backwards would get you an x to the power of 0, which doesn't make sense because you can't take the derivative of x to the power of 0 because it's 1 and is a constant and would not end up like this. Instead, we just have to dig in our brains and remember that the derivative of natural log of x is 1 over x. So when I see a 1 over x and I want to take the integral, I know it's going to be natural log. So I know that the integral of this is going to be 19 times the natural log of x plus c, right? Because we don't know if there's any constants. And then if I plug in e to the power of 3, I know it's going to equal 0. So 19 times natural log of e to the power of 3 plus c, did I say 0? That's a 63. That's a 61. Good Lord, I'm tired. I'm so sorry. Okay, but this should be true, right? So let's see, natural log of e to the power of 3. Well, that's easy. The natural log and e cancel out, and I can bring my 3 in front. So it's a natural log times 3, right? And then those cancel. Plus c equals 61. 19 times 3 is 30 plus 27 is 57. Therefore, c must equal 4, which means that our function is going to be 19 times the natural log of x plus 4. And that's it. I'm so sorry about how jumbled I am right now, and for wherever I messed up on problem 10 here. But I hope that overall this video was helpful and that most of my explanations made sense, or that you can make sense of them, even if they're not super clear. And yeah, thank you for watching.